problem we were solving. That problem had fluid flowing down a cylinder, and what we are interested in is the temperature profile, where the constant heat flux Q naught is provided. We look at what is the approximate solutions given by Lightfoot. So the velocity profile in this case is given by this. You can write this as Vz max. The capital R is the radius of the cylinder, and then for steady temperature distribution, we get that rho Cv and then we found that this would turn out to be rho Cv Vz dE by dZ. This we neglected the axial conduction term. We get K over RC d by drc, so RC d by drc. We show that this term, which would be the viscous dissipation term, can be shown to be proportional to RC square. So the very first of all, first we should consider the solution, and we consider that only because the problem of including the viscous dissipation effects makes the solution complicated. So let's first, as a first approximation, let's consider cases where viscous dissipation is neglected. Even then, the full solution is a bit more involved than what we will see. So we now consider the case where this is not there. So then what are we left with? Right, we are left with this. It must be possible to solve this, but what you consider again as the first approximation is only the large set solution. Before we do that, we have to non-dimensionalize. That's what we were looking at. So by non-dimensionalize, then let's use the non-dimensional temperature, which is given by this. So the temperature here at the inlet, the fluid is flowing in the temperature here as T is equal to T1 at Z equal to C. That's the boundary conditions. So we have to make the boundary condition also. So the solution is considered for viscous dissipation. The term can be there as it is, so that you can see what are the complications that arise when you include it. The boundary conditions we have to write T at RC Z equal to 0 is T1. That's one, because inclusion or omission of this term is not going to affect the boundary condition. Neglecting the axial conduction term will affect. Because when you neglect the axial conduction term here, which we have done, you have provided you one condition, that's considering a very long cylinder. So only one area effect has to be considered in terms of the boundary condition, and that we have provided. Otherwise, we have to have another boundary condition at Z equal to M, let's say. Right? So consider neglecting that. And for the RC, we need to provide two boundary conditions, and that is given by K dT by drc. At RC equal to R is given by Q naught. And the other condition, if we see the importance of that, T at RC equal to 0 Z is finite. You see why that condition is necessary when we solve the problem. So let me following axis because we're considering a very long cylinder. So that is why we need to introduce somewhat unintuitive non-dimensionalization of Z. So when you do that, well, all I have to do is to convert these equations in terms of the non-dimensional variable. So clearly, for instance, if I have t equal to t would be 2 naught r by k plus t1 times theta plus t1. dt by dz is q naught r by k, from which I can get dt by dz is this. But what I actually want is the derivative of the dimensional temperature with respect to the dimensionless distance. So I can write this as q naught r by k, right? The d by dz is all that's k by root cd r square, which is q naught by root cd dz max times r. That's what we get. So I have to substitute that there. And here, of course, we can do the same thing for the r direction derivative. So dt by drc would be q naught r by k d theta by drc, right? Which then is further equal to q naught r by k d theta by d sine and d sine by drc, which is q naught r by k. D psi by drc is 1 over r, right? So that would be 1 over r times so I get q naught by k times so I have another one of those. So I can now start writing the equation. So I get rho cv dz, which is dz max times 1 minus r over rc over r squared would be psi squared is equal to k over rc, right? So k over rc would be k over r times sine. So now I have to differentiate with respect to rc again. That can be written as d by d sine times d psi by d rc, which is 1 over r. So again I get another r, right? D by d sine. And then I have another rc here, which is psi times r. And then I have dt by drc, which I have calculated to be q naught by k yes. Oh yeah. Theta. light, before we neglected a light, and you will see what it is. So I have 4 mu dz max square. Rc squared by r squared is again psi square, and so I get 4 mu dz max squared by r squared times psi squared. So we have now to simplify this. Something dou t by dou z, dou cb, okay, dou t by dou z, that I have to get it. So that will be q naught by times so I have this, and then I have dt by dz, which I have written. Now I write it q naught by rho t r so this is what we get. So rho cb dz max will cancel. So and then I have q naught. So I have to, so when we write it again, q naught by r and 1 minus psi squared is equal to, so again I can get rid of 1 the r, so 1k will get cancelled. So we get again q naught by r sine d by d sine of sine d plus 4 I guess the idea is now if I multiply q by r times q naught, so I can get rid of this here. I can get rid of the q naught by r here. But here I would have to put r divided by multiply by r by q naught, and so I will get this. So this is plus 4 by r times q naught times psi squared. So I now got everything in terms of the dimensionless variables. K is probably missing somewhere. What happened to K? Is cancelled. There's something wrong. Okay, Z is there. They missed some K somewhere. K here also. Okay, anyway, so we have to sort it out. So what I have here is yeah, this is fine. The K seems to have dropped out, and so this is fine. So this is what the Brinkman's number is defined here as a very important number. This is the effect of the it's defined like this, and it's defined in this way because this is actually, if you see, the average velocity in this case can be easily shown to be dz max by 2. So this is actually the average squared by q naught r. So that is how it is defined. So you will get, so since the 4 is taken care of here, because V naught average dz max by 2, V average rather, the average velocity. So typically parabolic profile that you are very much aware of. So what you will get here, so this can then be written with this definition of the Brinkman's number. So you have a 4 on the numerator, you have 4 in the denominator. So I can have to write this as 16 times the Brinkman's number times sine squared. So we have finally, I can write it 1 minus sine back to the real variables, but here K is sort of compressed to as 16. So this is the final equation. It certainly looks much simpler than all of these other parameters there. So this is the final equation. And so now what he says, consider the case where the Brinkman's number is very small, right? And we give some conditions. They have given some conditions where that would be justified. So if I do that, then I'm left with this solution of this equation. This is still complicated because of the presence of the 1 minus x. So otherwise you can easily do by straightforward separation of variables, right? So what Bird would like to consider is a large set solution, and so they argue that large values of z, which means large value of the dimensionless number zeta, he says that the solution will have the following form. To justify it later, so he says then that the solution is represented by, this is very important, but this restriction, it can be given in this form. So what he is effectively saying is that for large zeta, that if you look at the derivative d theta by d zeta, it is a constant. So effectively, the differential at any point along the radial direction, right, actually it is increasing linearly with zeta. That's what it means, the temperature itself. So the derivative is constant. It means the even though the temperatures would be increasing because it's being heated by a constant heat flux. Right? Profiles of the temperature with respect to R will look very similar. They will all be parallel to each other because of the condition that the theta is very linearly with zeta. Which means the derivative will be a constant with respect to zeta. Right? So that is the approximation. He argues that this is the way it will be. So what I would say is we just proceed with this assumption, and then we have to now solve for psi. So that is the simple part. So we get 1 minus psi squared times d theta by d zeta, which is c naught. I'm writing that equation now. We're neglecting viscous dissipation effects. We're only considering the large zeta solution, which means the large z solution. So if I evaluate the left hand side, I have 1 minus psi squared, and d theta by d zeta will be a constant c naught which we have to determine. And then I have the d by d psi of psi. d theta by d psi, this is a big psi, that confusion in the way we say it. So this derivative would be because that's a partial derivative with respect to psi alone. This psi. Yes. Huh? 1 by psi is proceeding. Okay, I can write that. And in fact, for all practical purposes, now this turns out to be a total derivative because psi is a function of this variable alone. So you can write this as. So now it's very easy to integrate this, right? So all I have to do is to directly integrate. So we get d by d psi. C naught. So now first if I integrate, naught times, so this will be psi squared by 2. Psi squared by 2 minus psi cube, that has to be integrated. So that would be psi power 4 by 4. Now if we divide by psi, I can see not. And now again I have to, I'm sorry, I have an integration constant. So let me keep this. Psi d psi by d psi is this plus some constant c1, let's say. So I have integrated. So first integration is psi d psi by d psi is c naught psi squared by 2 minus c naught psi power 4 by 4 plus some constant. That's the first step. Second step, first I have to divide by psi. That would be this, and then here I make use of the okay, let's now integrate this, so we will get capital psi to be equal to c naught by 4, because there will be a psi squared by 2 and there is a 2, so minus psi power 4 by 16 plus c1 logarithm of psi plus c2. So now I have to make the boundary conditions. So boundary conditions are for the erase. What are the boundary conditions in terms of the dimensionless baby? Right? So first is d of, you see that one of the boundary conditions will not be satisfied in the final solution. So that is at z equal to 0, whereas what we are considering is the large set solution only, right? So anyway, first let's write down the solution to the boundary conditions. So first I have this. These are the three boundary conditions. T finite at t at 0 is finite, and then we get that d might k dE by dRc, RC equal to R is Q naught. Now these boundaries are independent of that particular special solution I'm considering. It will not satisfy one of these conditions. But I can now translate this to in terms of theta. So this will be theta of psi 0 is simply 0 because t is equal to t1 and z equal to 0. So theta would be 0. And then we get that the theta at psi equal to 0 theta is finite. And then the final one would be k dt by drc we have already shown is q naught by k d theta by d psi, and that is evaluated rc equal to r, which means it's evaluated psi equal to 1 is equal to q naught, which means d theta by d psi at psi equal to 1 is simply 1. There are no parameters in the boundary conditions also. This justifies the use of the non-dimensionalizing variable. Of course, it may be definitely useful for you, right, how to arrive at this, but by playing around with it, you can easily figure out. But the point is, once you are given this, then you should be able to derive the rest. I mean, difficulty if you write it the outset, because RC there is a characteristic length radius, but Z as well as T there are others. Because why this Q naught out by K is coming? No need for it. Simply to T minus T1, but T divided by T1 or something. But it is coming to simplify the problem in terms of the dimensionless variable. You might take a little bit of experience to infer that. This is a very standard approach. So given these dimension is big, it is a definition. Certainly, it should be possible for any one of you to obtain the final equation and the boundary in terms of the dimensionless space. That should be straightforward, just for differentiation and calculus. Right? So now we have got so first condition I will apply is the fact that t at 0 z is finite, which means t is finite, then theta also has to be finite. Theta has to be finite, and psi also has to be finite. At psi, the lowercase psi equal to 0. So clearly then this has to be at psi equal to 0. If this has to be finite, then clearly C1 cannot be anything other than C2. Right? So that is the first condition. So C1 equal to 0 I found one condition. The second condition I will find is theta at psi equal to 0 is 0. Is probably not going to satisfy. So theta at theta equal to 0 is certainly not 0. So I have to now not worry about this boundary condition because I am looking at the solution for large z only. Let's look at the next boundary condition. d theta by d psi at psi equal to 1 is 1. That I can certainly apply. D theta by d psi, as we have seen, is nothing but d psi by d psi. D psi by psi equal to 1 is actually equal to 1. Let's apply that boundary condition. We should be able to get one more. So these things is there. So this is gone. So I'm looking at this. So when I put psi equal to 1, right? So I get 1 equal to psi equal to 1 would be C naught times 1 over 2 minus 1 over 4. Now applying third boundary. Now, so clearly this is C naught times divided by 4, which means C naught is equal to 4. This is the second constant. There is a problem with the approach is that we are unable to use this boundary condition. It is not actually satisfying. Proposed form itself doesn't satisfy that boundary condition. So we cannot apply that boundary condition. So for that, to find so the problem is not yet complete. Even the large Z solution is not complete because we don't know what C2 is. C2 has to be found. We found the solution to only within a constant. So to find that, what words we are going to use is some kind of an integral condition, and I will explain that. It's somewhat important. They propose an integral condition. I'm not going to erase all of this. The integral condition is important to understand. By R then Q naught is equal to integral 0 to Q phi integral 0 to R rho CV times P minus P1 dz RC drc d phi. This is the condition that he proposes now to find the domain constant C2. Clearly you can see this is the integral over the surface of the cylinder, the flux that's integrated. So that's the heat coming in. Let's assume that the cylinder is heated from out. If Q0 is greater than C, right? So Q0 is greater than C, this is the heat coming from that. And this is the net change in energy as the fluid enters. So this is basically what is it representing? Suppose I fix, actually I have, this is okay. So let me fix the certain z, arbitrary, the cylinder is long, I will take an arbitrary value of z. And now what he is effectively saying is the fluid coming in, that's the velocity profile and temperature profile. So he is basically saying you have balance like this. So the fluid entering, this fluid leaving. So fluid leaving here is at temperature, I'm not saying it's uniform, just putting an arrow, the fluid is flowing out. So there is a T here, right? So function of RCZ, that is that T. T1 is the temperature at the entrance. So this is the envelope he is considering. And on top of it, there is a constant heating due to the external heat flux that is provided. It's basically an energy balance. All you have to understand is that it is an integral of the energy balance. If you see here, again here we might be making some approximation. So let me just clarify what kind of what is effectively doing is considering OCDE energy balance, right? And then I have, because it's only integral balance, of course in this case he's neglecting, otherwise you have to include that also. So now, if I now apply the integral balance to this envelope, so I have to integrate this over the whole volume actually. This is a volume integral that this equation represents. So I get rho Cv dV. This is actually dV. This is also dV. This is basically what he is doing. Now, how do you get this? So this is very easy to see, right? This I can write as minus. This is the heat that is transported by conduction. That is coming from the external source across the cylinder surface, right? So Q dot N is simply a constant, right? And it's coming in, right? So Q dot N is in the outward direction. So this will give me, but there is a, this is at the surface. This is all at the surface of the cylinder. This is this contribution. So N is again ERC, so minus, then I get minus K dT by ERC, at RC equal to R, right? ERC dot and then ERC, that's the integral that we are all familiar with, right? So this is the area integral with the normal to the cylinder surface, and we know that dA for that would be RC d phi dz. That is that term. Now minus K dT by dRC RC equal to R. There is a minus sign here, so that minus sign would cancel with this, and you get K dT by dRC RC equal to R. That is nothing but Q naught, right? So that would be Q naught, and that integral that integral is what? This integral is from, you get dz prime, so this is 0 to z and 0 to 2 pi. So I get a 2 pi out. And RC is also at RC equal to R, because this is on the surface of the cylinder, right? So R Q naught Z. that's exactly what I am getting here. You probably write it by inspection, integrated over the surface of the cylinder up to the point Z. Right? If you do it formally, then you take care of the sign. You have to understand if the sign comes, for instance, why do we have KdE by drc and RC equal to R equal to Q naught? This is a continuity of fluxes at the surface, right? Now Q naught has a sign. If Q naught is greater than 0, then heat is being provided from outside. It's being heated. So by our notation, that is what is the sign convention for Q. Whenever heat is input to the system, right, that should have a positive sign. So, in fact, I have not we don't have to commit ourselves to whether the fluid is being heated from outside or being cooled. That would depend on whether Q naught is greater than 0 or less than 0. Right? That would have to be taken into account. So, if it is being heated, whatever the magnitude of heat I am providing, that would come with a positive sign, otherwise it's a negative sign. Right? Now the heat flux outward from here would obviously have a, that outward flux is minus K dT by dRc. So again, if we want to look at the inward flux going into the cylinder, that would again have to have a negative sign, and you get this. You can easily verify the logic behind this. So once you have accepted this, then the formula remains as it is. Whether the fluid is being heated or cooled, you can easily verify that when the fluid is heated, you would have to put Q naught would be greater than 0, otherwise it would be less than 0. Right? So that is what I have. What about this? Right? So this is, we have clearly seen, this is now a volume integral. So it would have 0 to 2 pi, 0 to R, and 0 to Z. Right? So both CV, we've already seen this is Bz, right? Bz, which is a function of Rc alone. Right? And then dt by dz, that's the only term that would remain. We've already written it in our equation. That would be dt by dz, which of course is a function of Rc as well as use z prime as the dummy variable of integration. And then I have to complete the integral, so that would be Rc, drc, d5, dz prime. And using z prime as the variable of integration, doesn't consider a certain fixed value of z over which I am applying the. Now you can clearly see that the integral over phi will simply give me 2 pi, because none of the quantities are dependent on phi. So that I will get. Now what about this? This difference is coming because you can see that I can write this as 2 pi, and then I have 0 to R, drc, dz of rc, that can be taken out because this is independent of z. So I can do the integral over z first. That would be integral 0 to z, dt by dz, rc, dz prime, and of course I have an rc also that can be taken out. Here it is not rc equal to r, I cannot directly put because it's been integrated from 0 to r. This is basically takes care of the difference between what is happening. This can be regarded as a convective effect. The convective effect leads to the flow of the fluid. So there is a change in velocity profile as well as in the temperature. So the net change affected by this is what is being balanced by the heat that is given from outside. So it's basically an energy balance applied to an envelope covering the entrance and an arbitrary location Z. Right? So this can be easily integrated. dt by dz is just the derivative of t, right? With respect to this actually can be written, if you want, I can put the z prime here also. Then you can clearly see that this will give me the difference t of Z at Z, which is what this is, minus t at Z prime actually equal to Z, and t at Z prime equal to 0, which is t1, and so we get everything else in place. So this justifies the condition given by Lightfoot. Now what is left is really to, so having justified it, of course this means that the internal dissipation effects are neglected, otherwise you get a more complicated equation that involves a Brinkman's number. Right? So this is for the special case. So now you can easily convert back, and maybe I'll just write out the result because we're running out of time. You can go ahead and when you write it in terms of the dimensionless temperature and the dimensionless distances, what you will get is simply zeta is equal to interval 0 to 1 . This is the simple relation we get, because what is happening is that the constants are all getting taken care of, right? So Z is being replaced by zeta. We have to convince you, so you have to work it out and convince you that all the parameters are going to cancel, right? And then the 2 pi also will cancel here, and then t minus t1, that is what theta is. T minus t1 by q naught r by k. If I were to bring q naught r here, I would get that. Maybe k is also missing here. There must be a k here. No, k is taken care of. It's coming in the q naught, but something, I guess, yeah, we don't need the k. It's not going to come in. So 1 minus psi squared is coming from the velocity. We said max. That's a function of RC actually. Right? We said max times psi squared. And then you're getting a psi from this RC. So if you do this, then it looks like all the parameters get balanced out, and this is what you get. So now what you will do, you have to do is substitute this. So this would be C naught zeta, right, plus this sign, right, which we have found. So that would C naught is we have found to be 4 plus 4 times psi squared by 4 minus psi power 4 by 16 plus C2, which is what I have to find. Right? Of course, there is a zeta, but that should not, bother you with the integration. Because the integration is all over sine, right? So if you do this integral, you can check it out. That should give the value of the run-off of time. So the value of C2 turns out to be minus 7 over 24. So with this we will end today. We continue again on Thursday. There won't be any class on Wednesday. So Thursday we'll have a regular class. But let me just end with, we discuss this a little more detail. What he says is that for that is the dimension is z greater than 0.1. That is the measure of how large the distance should be. Theta is proportional to z, right? So that theta is greater than 0.1. That is the dimensionless distance in the z direction. If it is greater than 0.1, it can be considered safely as a large z solution. So this form will work, and we also say is that this form, that is this solution that we have calculated, predicts the dimensionless temperature to within 2%. So that gives a measure of the accuracy of the solution with respect to z, how long it should be. So if it is longer than 0.1, then you will get the beta to predict within 2%. So that's a good solution, right? We will see later on how to get the full solution and what are its implications.